final speaker today is Xuan Zheng from University of Bristol, but also working with Infineon in Bristol. He's a student there. Final year PhD student specialised in automating design verification through machine learning. Over the past few years, he has collaborated with Infineon in Bristol and successfully demonstrated the effectiveness of several novel test selectors in accelerating the convergence of functional coverage. And the title of the talk is Detecting Stimuli with Novel Temporal Patterns to Accelerate Functional Coverage Closure. Thank you.
So, hello, and today I'm going to introduce how to use machine learning models to find more efficient and effective stimuli to accelerate functional coverage closure. Can I have the?
So the clicker, yeah.
Oh, this one.
Yeah.
Thank you.
Yeah.
So the problem we are trying to tackle is the simulation redundancy caused by randomly selected tests. I mean, especially after the initial stage of test simulation, these randomly selected tests, they exercise the similar functionalities. So this is a kind of a waste of verification resources, because once the hit times are good enough, you don't want to hit time. You want to hit more new coverage, and it has been proved in the literature that tests being novel to those already simulated are more likely to bring novel coverage. So what's here I mean by novel tests, roughly speaking, are tests those are dissimilar to each other. So therefore, that's why we can use machine learning techniques, because in the machine learning models, we can have distance metric or novelty metric to measure the dissimilarity between them. And previously in Infineon, we have developed several test selectors for a signal processing unit that is more configuration based. The problem now is why we bother having another type of novel test selectors. So this is because for the previous selectors, both in literature and in Infineon, they only consider the novelty within the attribute values of a test. And they don't consider temporal dependencies and the correlations between stimuli at all. And this information can be very important in some digital designs like CPUs and the bus bridges. So now the new research question can be raised is how can we detect novel patterns? So before I answer this question, let me briefly explain what does it mean by novel patterns. So suppose now we have a test that only consists of a single attribute. And the figure 1 and the figure 2 describe how this attribute varies in time. And the figure 1 is the pattern we observed at the majority of simulated tests. And the figure 2 is the pattern we observed at an unsimulated test. And because of this spike here, so that's why we think the relevant test in figure 2 is novel. And also, as you can see, the value ranges of this spike is still between 0 to 100. That is also what we observed at the simulated tests. So that so that's why we think a test can both have normal attribute values and also novel temporal pattern. By the way, this is some artificial data. This is not some real data. And so in order to capture the temporal correlations between stimuli, we choose LSTM autoencoder and the transformer encoder, because these two models, they are designated to process sequential data. And here we will use these two models to reconstruct the generated tests. So which means they are trained to reconstruct simulated tests, and then they were used to reconstruct the unsimulated tests once the training finished. So here, why we don't use the supervised machine learning algorithms to predict the correlation between tests and the coverage. So this is because for coverage holes and the rarely hit coverage products, we don't have enough positive tests to learn from. I mean, although in research area, some people have proposed several solutions to address that, but none of them provides a unified solution. And therefore, we can use the reconstruction error as a novelty score to prioritize the test simulation. And here to evaluate the performance of our selectors, we choose a commercial bus bridge. And this is the bus bridge we used in trial core systems in Infineon for multiple masters, multiple slaves. So now we need to represent the tests in the format of vectors of attributes, and then pre-process them so that the machine learning models can digest them. So in our context, a test consists of multiple bus transactions. So basically, we are extracting the attributes from the bus transactions. And to be honest, we don't have some automatic approach to extract attributes. So we do this some feature engineering here. But the feature engineering here is not expensive. So this is because the features, they are from the bus protocol, which is defined very well, like these categorical features. Basically, we just need to filter out redundant features. Now, since we have the pre-processed dataset, now it's time for us to decide how we're going to drive a test to the selectors. I mean, we can't just blindly drive the entire test to a selector. So this is because this is not computationally efficient, and also this does not comply to the domain knowledge, because in the SRI bus bridge we can have 3 transactions in the pipeline at most. So therefore, we decide to use a sampling window to sample every 3 transactions as an input sequence driven to the selectors. And also, we will sample all the transactions within a test by sliding this sampling window. So in this way, a test can has multiple input sequences to a test selector. And now the question is, how do we combine the novelty scores of these input sequences for the entire test? So we basically just, we first calculate the novelty score of a sequence. That is the average value of the reconstruction errors for all the transactions in that sequence. And then once we have the novelty score for a sequence, we will square this novelty score. So this is because we want to put more weights on those novel sequences. And finally, we have a novelty score for the test, and we can use it to prioritize the test simulation. And so this is the dataset we generated for the experiments. So we have about 10,000 random seeds plus 2,768 golden seeds. And in the real project, the number of seeds to close this functional coverage is much higher than these numbers. And so the functional coverage model we were using pipeline, parallelism, and the data pacing coverage models. And the data pacing here basically means the number of cycles between each data bit in a burst transaction. And here we have 5 test selection approaches. The first one is the baseline random test selection. And we also have traditional autoencoder and the isolation forest. So these are the 2 previous test selectors that don't consider the temporal correlations between stimuli. And we also have transformer and the RSTM autoencoder in this work. So as you can see, during the initial stage of this test simulation, all the 4 smart test selectors, they are better than random selection, more or less. I mean, with the RSTM autoencoder has the best performance. But what we're really interested in is these simulation savings to reach these high coverage goals. And still, RSTM autoencoder has the best performance. And then comes the previous selector, isolation forest, and then over transformer encoder. I mean, so for the traditional autoencoder, it is even worse than the random selection after about 4,500 tests have been simulated. So here we set 5 high coverage goals to compare over approaches to the previous ones. So in terms of reaching 98.5 coverage level, the LSTM autoencoder can bring more than 13 times saving than that of traditional autoencoder, and also bring more than 2.6 times savings than that of isolation forest. And in terms of the computational expenses of all these smart selectors, they are not expensive compared to the net savings brought by them. So what I mean by net savings here is the actual saved simulation time minus these extra expenses. And here we're particularly interested in 98.5 coverage levels and the 99 coverage level. So this is because these 2 points are the places we start to think about use directed testing. And here 254 hours is under the continuous is the saved simulation time under the continuous simulation on a single EDA tool. Single EDA license, sorry. Yeah, if I translate this number into days, it's roughly 10 days continuous simulation. So for our future work, so first we want to use this novelty score as a proxy for coverage, so that we can use reinforcement learning to automatically generate tests without the need to frequent expensive simulation environment. And also we want to use graph neural networks because we think the errors and the nodes in a graph can help us to present more detailed those temporal dependencies between stimuli. And that's all. Thank you.
Thank you. Thank you very much. Are there any questions from the audience on that? You're currently doing this mainly for test selection rather than generation, correct?
Yeah, only test selection.
But do you think it could be extended to generation? You said about using the proxy. Would that help you do generation, do you think?
Yeah, we think so, because but it's very it's a long project if we want to verify that. At least maybe 2 years or 3 years.
Okay. Okay. I don't think there's any questions. So I think we're going to quickly just wrap up. So thank you very much. That was perfect. Before you dash off and get onto the motorway to get home, just please remember the feedback form. We do use these forms. We do try and improve things. So I think hopefully you can detect a slight improvement from year to year. I think we've got good feedback on the venue anyway. I think people prefer the venue to previous venues. That's good news. And we are thinking about a few innovations for next year. We'll probably send you some emails on them. But for now, if we can get the focus on the slides, please. Let me click a work.
Yeah, Mike, we can see your screen.
Yeah.
The slides are up.
Okay. So thank you very much for participating. Thank you for coming. Obviously, the sponsors wouldn't give us any money if you didn't come. So thank you for coming, and thank you for the sponsors as well. Cadence, Synopsys, AMD, Brecker, Siemens, Doulos, Lubis, and TechWorks, and ESF as well for Stu. Hopefully, we're going to work with Stu to get more students here next year, a bigger show of students. The presentations, the PDFs of the slides typically go on today or tomorrow. They're on very quickly. Recordings take a little bit longer, and they go on the website there. And it's hopefully very easy. If you actually just Google for verification futures test solver, you normally get there. Okay, but you'll get an email. I've been told there's no lack of emails. So you'll get an email telling you they're there. Ideas and suggestions for preferred topics for future verification events. As I say, we've got a couple of ideas for next year, but we'll see it slightly expanded, and we'll be sending those ideas for your feedback. Okay. If you've got anything else you'd like to see at the event, let me know. And we do listen as well, so we do have a Cocoa TB coming up as well because somebody asked for that, and it's there. It's actually there. There you are. It's for October. And no power verification in September as well. DV Club India is up and running again on ISO 26262 compliance on the 9th of July. And we have an event on verifying chiplet-based systems for anybody who's into chiplet-based systems, especially on UCIe, how to verify UCIe and maybe coherency across chips. It's becoming more of a challenge. That we're going to have an event on that. Verification Futures in Austin is on 12th of September as well. And for those who are FPGA oriented, there is an event in Reading on July the 16th on FPGA technology roadmap, and that's going to be based in Reading at Micron. Okay. And if you want to get involved in verification steering, DV, AIML in DV, RISC-V verification, I work quite closely with Mike Thompson of Open Hardware, and our training and design verification in RISC-V. And TechWorks will have an event coming up later this year about how to verify AI-based products. And that is my last slide, and that means it's 4:30, hopefully, and time to go home. So thank you very much for coming, and hopefully see you next year and online in between as well. Thank you.
Thank you, everyone. Thank you for joining.
Okay. Get feedback forms. We definitely want those. Tell us what you thought, how we can improve, how to make things better. And thank you to our speakers as well, of course. Thanks, Andy. Nice to see you again.